Welcome to the Deep Dive. We pull out the key insights from really fascinating sources, and today we're tackling a big one. The Nobel lecture by Subrahmanyan Chandrasekhar.
A giant in astrophysics.
Absolutely. And our mission here is to unpack how the universe's basic rules, these fundamental physical constants, actually control how stars live and die.
And how that leads to some truly extreme things out there. Black holes, neutron stars.
Exactly. Now think about atoms for a second. We have this pretty neat picture, right? A nucleus, electrons whizzing around, all following quantum rules. It feels elegant.
It is very elegant.
So the big question is, can we find that same kind of elegant simplicity when we look up at something as huge, as complicated as a star?
That's a great analogy to start with because atoms, you're right, we understand them incredibly well. Their size, their behavior. It basically boils down to just two combinations of natural constants.
Okay, like what?
Well, one gives you the Bohr radius. That's about half an angstrom, basically setting the scale, the physical size of an atom. Incredibly tiny. And the other combination, it relates to Sommerfeld's fine structure constant. This tells us about how stable the electron orbits are, especially when you factor in special relativity.
So these constants define the atom.
Pretty much. They explain why atoms have the size they do and why they, stick together.
That's fascinating for atoms. So can we do that for stars? Is there a stellar equivalent? What's the most important thing about a star, and can we boil it down to constants?
You absolutely can. And you hit the nail on the head. The most critical thing about a star is its mass.
Right, we always talk about stars in terms of solar masses.
Exactly. Usually multiples of our sun's mass, which is roughly 2 × 10⁻³ grams, a colossal number.
And stars seem to cluster around certain masses.
They do. Stars much, much smaller or vastly larger than our sun are actually less common. And what Chandrasekhar's work brilliantly shows is that there's a specific combination of the fundamental constants.
Like Planck's constant, speed of light.
Exactly those. Planck's constant h, speed of light c, the gravitational constant g, and crucially, the mass of a hydrogen atom h. Combine those in the right way.
And what do you get? What does that tell us?
You get a value, hCG 32, 1H2, which works out to roughly 29.2 times the mass of the sun.
29.2 solar masses. That seems specific.
It is specific, and it's deeply meaningful. It's not just some random number. It suggests a natural mass scale for stars woven into the fabric of the universe by these constants.
So it's like a cosmic sweet spot for stellar mass.
Kind of, yeah. It helps explain why we see the range of star masses we do. And this value, this combination of constants, it's absolutely fundamental to the whole theory of stellar structure and evolution.
Okay, so we have this natural scale for mass. But how does that play out inside a star? I mean, you've got this enormous ball of gas. What stops gravity from just crushing it instantly?
That's the constant battle inside every star. It's this incredible balancing act. You have gravity always pulling inwards, trying to collapse everything.
Relentless.
Totally relentless. But pushing outwards, resisting gravity, is the internal pressure.
And that comes from?
2 main things. One is just the thermal motion, the incredibly hot gas particles bouncing around. Think of it like the pressure in a balloon, but way hotter.
Okay, and the second?
The second is radiation pressure. The light, the photons generated deep inside the core, they get trapped and bounce around, exerting their own outward pressure.
Well, I remember reading about Sir Arthur Eddington's work on that. He really emphasized radiation pressure.
He absolutely did. He had this famous quote about it being essential to the very happening of the stars. He saw how critical it was.
So it's gas pressure plus radiation pressure fighting gravity.
Exactly. And there's actually a theorem, a general relationship in stellar physics that connects the pressure needed at the center of a star to its total mass to keep it stable.
And this lets you figure out how important the radiation part is.
Yes. It allows us to quantify the fraction of the total pressure that comes from radiation. We often call this fraction 1 minus beta.
Okay, and Chandrasekhar's lecture gives an example, right? For a star like our sun, what does that fraction look like? Is radiation pressure a big deal?
Well, for a star with the sun's mass, the radiation pressure deep in the core is typically less than, say, 3% of the total pressure.
3%, that sounds tiny.
It does sound small, doesn't it?
Yeah.
But even that small percentage is absolutely crucial for the star's overall structure and stability, especially as stars get more massive. And it links back to that characteristic mass scale we talked about, the 29.2 solar masses. It's all part of the same physical theory.
It's amazing how interconnected it all is. Now, you mentioned stars getting into difficult situations. Chandrasekhar discussed a paradox from Eddington. A star will need energy to cool. What on earth did Eddington mean by that?
Yeah, that's a wonderfully counterintuitive statement, isn't it?
It really is.
It came about when astronomers started observing white dwarfs, like the companion star to Sirius. These things were found to be incredibly dense.
How dense are we talking?
We're talking densities of maybe 100,000 to 10 million grams per cubic centimeter. Just fantastically dense. Imagine packing the mass of the sun into something the size of the Earth.
Wow. Okay.
So Eddington looked at this and wondered, well, if a star has burned through all its nuclear fuel, all its subatomic energy, as he put it, and it's squeezed into this incredibly dense state, how does it ever get out of that state? How does it cool down and expand? It seemed like it was trapped in an awkward predicament.
Like it couldn't possibly become normal matter again.
That was the puzzle. R.H. Fowler put it even more clearly later. He asked,
Huh.
what if you took this super dense white dwarf matter, which theoretically has less energy than normal atoms at absolute zero temperature, and you just removed the immense pressure holding it together?
What would happen?
Well, the calculations showed that the internal electrostatic energy, the repulsion between electrons and nuclei, would vastly outweigh any kinetic energy from heat. So if you just let it go, it couldn't simply expand back into a gas of normal atoms. It seemed stuck.
A dead end, cosmically speaking.
It really looked like one. But then Fowler, back in 1926, published this absolutely seminal paper called Dense Matter.
And this broke the deadlock.
Completely. He introduced concepts from the then-new quantum mechanics, specifically Fermi statistics, and the idea of electron degeneracy. This was a totally new way to think about pressure in these extreme states.
Electron degeneracy. Okay, what is that exactly?
So in normal matter, pressure comes from particles bouncing off each other, right?
Yeah.
Temperature-driven. But in a white dwarf, the electrons are crammed together so tightly, I mean unbelievably tightly, that a quantum rule called the Pauli exclusion principle becomes dominant. It basically says that no two electrons can be in the exact same quantum state, same place, same momentum, same spin.
Okay.
So even if you cooled the star down to absolute zero, the electrons are forced into higher and higher energy states just because all the lower energy slots are already filled. They can't all just sit still at the bottom.
Like musical chairs, but for electrons?
That's a decent analogy. And this inherent jostling for quantum states creates a degeneracy pressure that has nothing to do with temperature. It's purely a consequence of quantum mechanics and density.
A quantum pressure pushing back against gravity.
Precisely. And for electrons that aren't moving too close to the speed of light, what we call non-relativistic, this degeneracy pressure has a specific relationship with density. Pressure goes up as density to the power of 53.
P proportional to rho to the 53.
You got it. And that specific relationship is what allows stable white dwarf stars to exist. It provides just the right kind of pushback against gravity.
And Chandrasekhar showed this wasn't just theory, it matched observations.
He did. He calculated that for a typical white dwarf, say 1 solar mass, this theory predicted a radius and density that were spot on compared to what astronomers were actually seeing. It was a huge success.
So problem solved. All stars just end up as these quantum-supported white dwarfs.
Well, that was the initial thought, yes. It seemed like the universal endpoint for stars after they ran out of fuel.
But I sense a but coming.
There's always a but in astrophysics, isn't there? The but comes when you keep piling on mass, making the star even denser.
What happens then?
Then, those crammed-in electrons are forced into such high-energy states that their speeds get incredibly fast. They start approaching the speed of light. They become relativistic.
So Einstein's relativity starts to matter even for the electrons inside the star.
Exactly. And when electrons become relativistic, their equation of state changes. That nice pressure-density relationship we had, P proportional to rho to the 53, it shifts.
How does it shift?
It becomes P proportional to rho to the 43.
5/3 becomes 4/3. Okay, why is that change so important?
It's critically important because pressure now increases less steeply with density. As gravity tries to crush the star further, the relativistic degeneracy pressure doesn't push back quite hard enough anymore. It loses the battle.
The support gives way.
Effectively, yes. The consequence is profound. There is a maximum possible mass that electron degeneracy pressure can support, no matter how dense it gets. Above that mass, collapse is inevitable.
And that is the Chandrasekhar limit.
That is the Chandrasekhar limit, the ultimate mass limit for a stable white dwarf star.
Mind-blowing. So how does this limit shape how stars actually evolve? Is there a rule for which stars get to become white dwarfs and which ones don't?
There is a key criterion, yes, and
Right.
it links back to that radiation pressure idea. For a star's core to even become electron degenerate in the first place, its internal radiation pressure needs to be relatively low specifically, less than about 9.2% of the total pressure.
9.2%.
Another specific number.
Another crucial threshold. It basically divides stars into two main evolutionary paths based on their starting mass.
Okay, path one.
Path one is for the less massive stars. Let's say, roughly, stars born with up to maybe 6 or 8 times the mass of our sun.
Okay.
In these stars, the radiation pressure stays below that 9.2% limit. As they age, they burn through their fuel and develop an electron-degenerate core made mostly of carbon and oxygen. This core grows.
Until its mass hits the Chandrasekhar limit, which, for that composition, is about 1.4 times the mass of the sun.
The famous 1.4 solar masses.
That's the one. And when the core hits that limit, degeneracy pressure fails. But what happens next is that the incredible compression triggers runaway nuclear fusion of the carbon and oxygen.
Kaboom.
Big kaboom! A type ES supernova. The whole star is obliterated, no remnant left behind.
Wow. Okay, so what's path 2 for the heavier stars?
Right, stars born with more than, say, 7 or 8 solar masses. In these giants, radiation pressure is much more significant. It's above that 9.2% threshold.
So no stable degenerate core forms early on.
Not in the same way. These stars go through a much more complex series of burning stages fusing carbon, the neon, oxygen, silicon, heavier and heavier elements in concentric shells dip inside.
Like an onion.
Exactly like a cosmic onion. They also lose a lot of energy through neutrinos, which just stream out of the core. Eventually, they do form an iron core, which does become degenerate and approaches the Chandrasekhar limit.
But it's different this time.
It's different because it happens much faster, and the core is surrounded by all these shells of heavier elements. When this iron core hits the limit and collapses because iron can't fuse to release energy, it doesn't trigger runaway fusion like in the less massive stars.
So what happens instead?
The core collapse is catastrophic. It collapses down, bounces back, and sends a shockwave ripping through the outer layers of the star.
That sounds like a different kind of explosion.
It is. That's a type 2 supernova, a core collapse supernova. And this time, something is usually left behind.
Ah, the remnant. What is it?
If the core's mass isn't too enormous, the collapse is halted by another kind of degeneracy pressure, neutron degeneracy pressure. You form an incredibly dense neutron star.
Often around 1.4 solar masses, right? Like the pulsars.
Precisely. The masses we see for neutron stars, especially in binary pulsar systems, line up beautifully with that Chandrasekhar limit for the initial core collapse.
And if the core is even more massive, if even neutron degeneracy can't stop it,
then there's nothing left to stop the collapse. Gravity wins completely. The remnant collapses indefinitely, crushing itself down.
to form a black hole?
To form a black hole.
Oh.
The ultimate victory for gravity.
It's just incredible how this one limit, derived from quantum mechanics and relativity, dictates such dramatically different fates. But Chandrasekhar's lecture didn't stop there, did it? He talked about other instabilities, purely from general relativity itself.
That's right. Even beyond the Chandrasekhar limit, Einstein's theory introduces new ways for massive objects to become unstable, purely due to the way gravity warps spacetime.
Like what?
Well, one type is called vibrational instability. In good old Newtonian physics, a star is stable if its material is, stiff enough if it pushes back hard when squeezed. We measure this stiffness with something called the adiabatic exponent, gamma 1.
Okay.
But general relativity adds a twist. It says stability doesn't just depend on stiffness. It also depends on how compact the star is, how close its radius is to its Schwarzschild radius.
The radius of the event horizon, if it were a black hole.
Exactly. GR predicts that no matter how stiff the star's material is, if you squeeze the star down so its radius gets too close to its Schwarzschild radius, it will become unstable and collapse.
So gravity itself triggers instability just by being strong enough.
Precisely. For example, even with a very high stiffness, gamma 1 equals 53, a star becomes vibrationally unstable if its radius shrinks below about 2.4 times its Schwarzschild radius. There's a fundamental limit imposed by GR on how compact any stable object can be.
Gravity setting its own limits.
Hmm.
Amazing. And this applies to spinning stars, too. Or do they have their own issues?
They have their own unique relativistic issues. That leads to the second type, secular instability due to gravitational radiation.
Gravitational waves coming into play.
Exactly. GR predicts that if you have a massive object spinning rapidly and it develops even a slight wobble or asymmetry, it will radiate gravitational waves.
Ripples in space-time.
Right. And radiating those waves carries away energy and angular momentum. The star loses its spin energy.
So it slows down.
It can lead to instability. Think back to classical physics. Lord Kelvin suggested that a rotating fluid blob, like a star, might prefer to become a sort of flattened ellipsoid shape if it loses energy due to viscosity. Gravitational radiation does something similar, but it drives instabilities in specific ways, particularly through what are called non-axisymmetric modes, or Dedekind modes.
So the spinning itself can make the star unstable via gravitational waves.
If it spins fast enough, yes. These instabilities become stronger for rapidly rotating objects and effectively set upper limits on how fast things like pulsars can spin. If they spun much faster, they'd rapidly lose energy through gravitational waves and become unstable or slow down.
So we have the Chandrasekhar limit from quantum mechanics and relativity, and then these extra layers of instability purely from GR itself. It really feels like the universe is pushing massive stars towards becoming black holes.
That's a very good way to put it. The laws of physics, as we understand them, seem to make black hole formation an inevitable outcome for the most massive stars. They really must exist out there in huge numbers.
So what does GR tell us about the black holes themselves once they form?
Well, fundamentally, a black hole is defined as that region of space-time enclosed by an event horizon, the boundary from which nothing, not light, nothing can escape. Far away from the black hole, space-time becomes asymptotically flat, meaning it just looks like normal empty space.
Okay, the point of no return.
Exactly. But here's where GR gives us something truly astonishing, almost unbelievable.
What's that?
For black holes that have settled down, that are stationary and isolated, Einstein's equations in a vacuum have a very limited set of solutions. In fact, there's essentially only one unique family of solutions that describes these black holes.
One solution for all black holes.
One family of solutions characterized by just two parameters. It's called the Kerr family of solutions, named after Roy Kerr, who discovered it.
Wait, just two parameters describe any stable, isolated black hole? What are they?
Its mass and its angular momentum or spin. That's it.
Mass and spin. Seems incredibly simple for something like a black hole.
It is almost disturbingly simple. Think about any other macroscopic object, a star, a planet, you, me. Describing us completely requires specifying countless details about composition, structure, temperature, magnetic fields. It's incredibly complex.
Right.
But a black hole, according to GR, once it settles down, forgets almost everything about the star that collapsed to form it. All the complexity is swallowed. All it remains, detectable from the outside, is its mass and its spin. All black holes with the same mass and spin are utterly identical.
No hair, as they say.
That's the no-hair theorem, in essence. It means black holes are defined purely by the warping of spacetime, dictated by their mass and spin, derived from the most fundamental equations of GR. This led Chandrasekhar to make a remarkable statement in his lecture. He said that because their structure is defined only by our concepts of space and time, black holes are almost by definition the most perfect macroscopic objects there are in the universe.
The most perfect.
And because they are described by just these two parameters arising from this unique Kerr solution, they are also the simplest objects as well.
Perfect and simple. That's quite a description for the most mysterious objects we know.
It is. And even though the description is simple, the physics around a Kerr black hole, the space-time itself, is incredibly rich and complex mathematically. It allows physicists to solve fundamental equations exactly in that warped space-time and predict all sorts of fascinating phenomena when matter or light interacts with the black hole.
Wow. So we've gone from these fundamental constants, setting a scale for stars,
Through the quantum pressure holding up white dwarfs, up to the Chandrasekhar limit,
then the relativistic instabilities forcing further collapse.
leading inevitably to these black holes described with such profound simplicity by general relativity.
What an absolutely incredible journey through physics, all laid out in Chandrasekhar's work.
It truly is. And Chandrasekhar himself concluded his lecture by reflecting on this journey, particularly the study of black holes. He said it convinced him of the truth behind old philosophical ideas.
Which ones?
Ideas like, the simple is the seal of the true, and beauty is the splendor of truth. He found that deep simplicity and mathematical beauty in the description of black holes.
And that simplicity, that elegance, really does come through, doesn't it? The universe's most extreme objects may be governed by the simplest rules in the end.
It seems that way.
So here's something to leave you thinking about. If black holes, these incredibly massive, gravitationally dominant objects, are indeed the universe's most perfect and simplest macroscopic structures, what might that imply about the fundamental nature of reality itself?